go ahead and do what I consider some short-term analyses. I'm not going to be doing MSCs or anything like that. So there's a couple of questions we have to address. The first one is, this is almost an emotional one. This is sort of psychological. You know, I come from the premise that we should use as much data as possible to reduce variance, but ultimately, somewhere along the line, you have to get to a point in your life where you say, actually, stationarity isn't right? And we have to break with that. Once you've got through that emotionally, which is hard, we then got to look at all the different parameters in our models and ask the question, you know, which of them are likely or certainly going to be a function of time, either just randomly or related to environmental variability. So I've done a first cut here. How many of these things do I think change over time? I think growth is a given. I mean, growth is only constant when you don't look at it, right? The moment you look at growth over time, you see changes. And Christine Stavitz, who was going to be here, but I think she's online, her PhD was all about that. So I would put that in the certainly category. You know, if you get growth data, you're going to see changes over time. Selectivity is definitely, every fishery I've been in, selectivity has changed over time. Mean recruitment, probably the most, in some sense, the most influential, perhaps for natural mortality. Pretty likely Cody Suswolski's work on, Tatjana Vertprey's work on looking at production functions and things like that. Catchability, particularly in surveys, probably. A number of the North Pacific surveys now allow for time variation in the survey catchability, and that's related to how the fish are reacting to the changing environment. And then the last one, which I'm sure Grant is saying, what are you talking about, you idiot? In brackets, once I graduate. Natural mortality. Now, I'm thinking of this really in a single species context rather than a multi-species context. And the difficulty with natural mortality, in some sense, compared to the first four, is natural mortality in a single species assessment is really never seen, right? It's always inferred. Whereas in a multi-species model where you've got diet data, you're observing natural mortality. And then the question is, what does this all imply for harvest control rules and reference points and stuff? And I think I'm gonna really not get too deep into this question, but it is in fact the most difficult question we as scientists are facing today, because and hopefully Grant will answer this in his PhD, but if tomorrow the North Pacific Council says, it turns out species interact biologically. Huge shock, because we don't do that. They decide tomorrow we're going to use multi-species models to manage every fish stock in the North Pacific. Why not? What would we do? We have no notion of what happens to our control rules as the environment is changing, right? So even if tomorrow we want to use Atlantis as an estimation model, which I'm sure Albie would probably not support, we wouldn't know how to set the reference points, because BMSY is a multi-species concept only. So I'm going to touch on this, but I think this is a really important point that no one is spending enough time on. We're pushing very hard to do the analyses I'm talking about, but not necessarily their consequences. So I'm not going to talk about the ACLIM project. You've all probably seen ACLIM in some shape, form, or presentation. Kirsten Holzman has given some awesome presentations. I could never pretend to be nearly as good as she is, so I won't. But this work that I'm talking about is funded in part by the ACLIM project, and so is Martin Dawn online? So yeah, so Martin, it turns out, has my skill in terms of producing pretty slides. We don't have the GoACLIM version of this yet. I'm hoping we can. I mean, we just got black and white slides, right? Compared to this. That's why their project's $1.5 million and ours is only $1 million. So We need a logo and we need some better slides. Anyway, but the point here is that there is a very large project that is looking at this problem across multiple models and for multiple objectives. So on the right, left-hand side of the slide are the types of processes that are being explored in both GoACLIM and ACLIM. And on the middle column are the types of things that those models may be able to predict. I'm actually going to only focus on 2 effects on the left-hand side and 2 effects in the middle. I'm looking at climate effects on growth, and implicitly on condition factor, and survival and hence abundance. So I'm really focusing down. I'm not talking about food webs. I'm not going to talk about distribution. And the outputs I'm interested in is how does this change our perceptions about quotas, catches, revenue, and future biomass. So a very restricted set of objectives within the context of these single species models. Once Albie gives his presentation, he'll have red everywhere, right? You can do anything. Especially when half the stocks crash. The good news is mine don't go extinct in the past. They go extinct in the future, but Atlantis, it's always an interesting question. How many stocks aren't there now? Okay, so we're going to talk about some general methods. So in many respects, this is probably the most important slide I really want to get across. And that is, we've actually developed a lot of extended single species models going back probably 20 years ago now, where we impose a environmental driver. What I'm not seeing, and I guess I'm to blame as much as anybody else, is I haven't seen a holistic framework within which that process occurs. And I am thinking about the Ram Myers, the failure of doing this for decades. So the approach I'm going to take is given here. I'm going to start with a single species assessment that's approved and used for management. I'm going to then look at my biological parameters in the model and ask somebody smarter than I am, what do we know mechanistically between those parameters and environmental variables in principle, okay? So, Baptiste is smarter than I am, so he knows that the growth rate of cod is related to copepod abundance, right? We need to know that. We need to put that down at this point in the analysis. And the first thing we're going to do is we're going to focus on the past. What can the past tell us about these relationships? And the third step here is actually very important, and I've put it third, not second. What am I getting at here? So what the third step is to put environmental variables into the model given step 1. Right, so you start with the hypothesis, then you define the variables. Because what you're going to find, as is the case for copepods in the Gulf of Alaska, am I correct that we don't believe the copepod numbers anymore, following your discovery of the? Yeah, so I hope I get that example right. So basically, we know we want to put copepods in the model, right? The hypothesis is copepods. The reality is we don't actually have an index of copepods. So there's going to be a whole lot of hypotheses that get culled out. And what I'm seeing in the field is people jump immediately to what can we estimate? We can get SST. So let's stick SST in the model because we've got it, right? And I think that's a really bad way of doing things, right? You want to start with what are the drivers? Can we quantify them? Often you can't quantify them and you need to be honest about it. Then we're going to apply model selection. We're going to calculate reference points like FMSY, except I'm not going to calculate FMSY. Then we need a forecast into the future, right? So right now, all I've done is I've taken a stock assessment, added some variables, and calculated FMSY. Now I'm going to project in the future, and again, I'm going to ask Kirsten and Albie and Grant for projected environmental variables. And here we're going to start to bifurcate. So we're going to bifurcate a number of times. By bifurcate, I mean we're going to increase the number of models that we've got. So if we start with one stock assessment model, We've got a whole lot of hypotheses about what could be driving the dynamics. So we've now got a whole lot of models with different environmental variables. We're now going to forecast, right? And so let's pretend that SST is the winner, which it often is. For the Bering Sea, I'm going to have 6 ways of forecasting into the future, right? There are three Earth system models and 2 emission scenarios, right? So can you see the little tree getting more and more expanded? In the Gulf, we've got fewer options. We've still got 2 climate scenarios. We're going to then, so we're projecting our model forward. Let's say we choose emission scenario, whatever, MyROC 126, if there is such a thing. That'll give you a projected set of catches, right? And I'm going to show you how sensitive projected catches are to those factors, right? So let's say you got stock assessment model, hypotheses, environmental variables. Each of those lead to 1 catch series. Okay, that's uncertainty, right? Problem is we don't know which model is correct. We have model selection, so hopefully we remove the ones that are stupid. We don't know which model of the system is right. We probably don't even know which emission scenario is even most likely at this point. So what we're going to then do is we're going to ask the question, what would happen if I managed under 1 catch series when a different catch series was correct? And that's going to be one of my measures of uncertainty, is the between model implications of managing under a catch series, because we manage under catch series. And then I'm going to get a little more complicated. I'm actually going to bring in process and observation error. So I'm going to quantify as many uncertainties as I can and hopefully conclude that I know something. Okay, forget the slide, it's too small. I can see it in this is just the flowchart version of what I've just seen. The idea is to show that I can create flowcharts. Okay, so I'm really into slide designer, which gives you truly stupid designs, but you know, at 3 o'clock in the morning, this looked pretty good.
I noticed these slides are a lot more artistic than usual.
Well, there's a button now.
Shit, now we're discussing whether you were using the same PowerPoint template from 2001.
Yes, I've actually changed it a little bit, but not much.
And your presentation is still numbered.
Yeah. Well, no, no, that's for classes. But no, the papers are still numbered numerically. I'm on 487.
I'm going to go by 60. You better go by 60.
65, I've got to get to 500 published papers. But this is not important. It's agreed. There is a lot of wine involved, so it actually is very important. Sabrina.
So you had mentioned that you're also looking at some sort of condition data, right?
It's only implicit for these models. They don't. Because you're changing weighted age and not length age, you're implicitly changing condition. But I haven't modeled condition implicitly.
Yeah, and I know you never really usually get good weight data to actually, but there's a lot of information there about how the environment, like an individual's perception of the environment based on their condition, right? That accounts for like obviously temperature changes, the metabolic, but competition for food resources are going to, there's going to be a lot of reasons why the environmental variable is not going to reflect what's happening in the growth.
So I haven't done that, and I haven't even tried to. So this is I'm double dipping in talk. So this is anyone doing the age structured class with Ray. This is lecture 12 or something, so you can skip that lecture. So I'll touch on stock synthesis stuff. In principle, you can make the A parameter of the length weight regression a function of time or of environment. So if, for example, SST affected the condition parameter, which is the A parameter, you could put that in the stock synthesis, but I didn't do it.
Yeah.
Of course, you need some data. Okay, so I'm going to talk so what I'm going to do for the rest of this is I'm now going to get into each of the layers that I highlighted. I'm going to start with the assessment models to start with. And just to say that I didn't do any of the hard work to do these assessments. Steve Barbeau and Pete Carlson did all the hard work. but I'm an academic, so I just take that. Each of the two assessments has got a long history, and to get to these assessments, I'm just going to take them as such. So for COD, there are actually 4 assessment configurations. So the assessment is actually based on a model average already, and the features of that assessment are that the 4 models. There's sort of something called 19-12A, and you have to speak North Pacific Council to know what a model, how model numbers are created, but that's the base model. 19-12 allows for survey Q to change over time, just randomly for the moment. So think of it as a random walk in Q. There's 21-1, which includes dome-shaped survey selectivity, and 21-2, which is fisheries CPU. All of the models allow, all of the models allow for time varying length at A-min. So if you're doing your stock assessment class, L-A-min is time varying, which basically means some cohorts are growing faster than others, because they're all reaching the same L infinity, but some are starting earlier and some are starting later. And then there's hordes of fishery selectivity blocks as the fishery has changed over time. For Gulf of Alaska cod, very similar in many respects, except there is one model, but there are 3 fleets. So in the Bering Sea, there's 1 fleet. In the Gulf, there are 3, 2 surveys. What's cool about this assessment is it already includes environmental drivers. In particular for M, you'll all remember the marine heat wave in 2014 to 2016. What's modeled here in the assessment is a block change in M. So M is constant until 2014, and then it streams up, goes constant for a while, and then goes back down to the reference level. Okay. Note that that's fine, and in fact, it's a really good model, but it's really hard to forecast a block, right? I mean, you've got to know when the next bump is going to happen. So we'll talk about what to do with that. Survey catchability, I believe it is actually the long line survey. It says LL, which I thought would be long line in the file. LL, would that be long line for you guys? I would have thought what Jim told me. Jim Iannelli told me I didn't know what I was talking about. But already that survey catchability is linked to bottom temperature. And one of the interesting things this was sort of part of the lessons that I'm learning. So I've got what's almost becoming the official temperature. So there's an official set of ROMs output that we use. And I can't work out, I think this is bottom temperature actually from the survey itself. And there's certainly a strong correlation, but when I'm talking about temperature, there are going to be multiple definitions of temperature because it's not unique. So hopefully, as these projects move forward, we establish a common way to do temperature, because if I put temperature in a model and Terence does, we hope if they're the same, supposedly the same SSTs, that they're the same numbers. But right now, that isn't the case. And there's also lots and lots and lots of time varying selectivity. Yeah.
When you are incorporating temperature,
Yep.
I mean, there's a spatial component to
Correct.
that, correct? So you're, all right, notice.
Yeah, so I think I do touch on that, but if I don't, for Bering Sea pollock, I've worked with summer temperatures in the so-called southern eastern Bering Sea. For Goa cod, it's the 2 blocks to the west of Kodiak Island, 610, 620, and that was down to 300 meters, and in the summer, if I remember.
That's why not all the temperature time series are the same.
Right. Except that even the number, if you read a lot of papers, how many of them actually define where they got the temperature from is depressingly low. It just says we use SST, as you said, there are like a lot of ways of doing that. It turns out a lot of them are correlated, and I'm using most of these as indices, so I'm sort of in good shape. People like Albie, who are using temperature in absolute terms, that becomes much more of an issue. Any questions online, or has everyone left already?
Just a reminder, you can put questions in the questions bar, or you can raise your hand and unmute you.
Um,
One more question,
Yep.
just a clarifying question. In the Eastern Bering Sea cod model, so there's only one fleet?
Yeah.
So they're only looking at trawl?
no,
It's just combined.
all the gears are combined into a single fleet.
How does that work with selectivity?
It changes a lot over time. Yeah, so that is definitely an issue. But the good news is, I think they're not too worried about parameters because they got 400 already for most of these models. And once I add what I'm going to talk about now, it just gets better. The models that we've looked at based on sort of hypotheses that we've been given. So for the cod model, I'm looking at 3 alternative environmental models. First one is just a null model that says environment isn't related to anything. The second model allows for temperature effects on growth. The third one allows for temperature and pH effects, which be SST, not STT, which I think is the salmon technical team. I was writing this during the Pacific Council meeting. For those who remember Stephanie Thurner, she's now on the STT, I think. She now works with the tribes. But
I have a question on
yes.
Caitlin Shotwell asks, for the GOA cod environmental options, did you reference the GOA cod ESP, ecosystem and socioeconomic profile?
I'm sure someone did. It wasn't me. I should have. I think Steve Bobo is part of that, and this someone came from him. So that there's 3. Those are the options. For cod, it's a little more complicated. I looked at what's the effect, but yeah, if Katie, there are other hypotheses I missed, I'd love to hear them before I ask you guys for more environmental insights. So the options I looked at are firstly natural mortality, and the 2 options I looked at are block. So 2014 to 2016 being a block, or SST. And the reason I was interested in SST is SST after Grant and Albie did magic to the extraction, has a sort of peak in 2014 to 2016. But it means that I can forecast, right? I've got SST going into the future. Also looking at growth and recruitment. For recruitment, I also looked at bottom temperature and bottom pH. And then, as I noted here, that I used the NIMS boxes 610, 620. The one thing that I'm doing here, which I think is, good practice, is I'm testing the same underlying biological hypothesis for both stocks. And the reason I'm doing that, apart from natural mortality, is I'm trying to avoid spurious correlation. So my meta hypothesis is if growth is affected by temperature, it should be affected by temperature in multiple areas. It shouldn't just be affected in one area. I can envisage why the size of the effect might be different, but the sign shouldn't be the other way around. So what I'm trying to do is coming up with this idea of a process for selecting these things instead of what I call the machine gun method, which is.
But if they're at different, if they're at different ends of their range, like with a lot of temperature effects, there's an optimum.
Right.
So if you're at the northern end of your range, then it's going to be positively correlated with climate change. It's also,
I can see exceptions, but I guess I'm looking for something as a default. So a priori, if I got differences, I'd be more concerned than if I got consistent. But I agree, dome shapeness is nice. That's it. Stock synthesis doesn't allow you to. It turns out, and it turns out, although I have to. So for all people to know, this is a pirate version of synthesis. This is the Andre synthesis, which it turns out I tried to pirate that dome shaped into it. The term deep in stock synthesis, like where those environmental covariates come in, is really deep. It's not one line of code to fix it, it turns out. And I gave up. You probably know where in the code it is.
No, I would just after.
Yeah, that doesn't get. I tried that. I think Rick's comment was, yeah, you fix it up and send me the new code and I'll incorporate it. Okay, so just to give you some actual Oh, I was going to say data, but in fact, there is no data here. It's all model output. So this is my slide that says the Gulf and the Bering Sea are bad places to be in the future. This is the Gulf. The dots are hard to see. This is sea surface temperature. The dots are the SSP 126, and that increases. Remember we're already over here, right? So there's 2014 to 2016. Yeah, so projections start in 2021.
Technically, they start in 2015.
Right, but you've got
the Hindcast is until 2020, then 2020 to 2100 is all projections.
So this is all projection, and the difference between this is 585, which is the more pessimistic, if you want to call it, scenario, and you can see temperature increases. This is bottom temperature. This is pH. pH, it's hard. The scale is obviously a lot different, but you can see under the increasing temperature regime, you get quite a big drop in pH. And a small drop in pH is actually not that small. These on crabs, at least, they don't dissolve. Now, this is a horrendogram. Never show this to anybody else. So what we've got here, these are projections for. There's actually 9 models in this particular slide, but with a big squint, you can see that temperature increases. Sabrina disagrees. She's squinting.
Yeah, well, we can't even read your
Yeah,
actual.
what are the axes?
Okay, so this is bottom. I'm going to give you the important ones. Bottom temperature, sea surface temperature, pH. So pH goes down, bottom temperature goes up. SST goes up. This is winds, which is to do more with northern rock. Okay, so for those who've never used stock, so this is lecture 13. You're actually in Fish 555 now, Terence. The cool thing about stock synthesis is actually remarkably easy to allow variables to be related to environmental covariates. So this is the parameter section. This is the natural mortality. This is growth. This is for cod. So what I've done here, this is the environmental link parameter. So I've chosen 2 because growth is multiplicative, and 104 being the link to the 4th environmental variable. And then here is, so I've got a link to the environment as a deterministic function, but I've also got random variation in length. So I'm estimating a long-term trend related to the environment, but I'm also allowing for stochastic variation in L15, L1.5 as well. For this is for the R0 parameter. Here I'm assuming it's additive because it's log space, and it's related to environmental variable 5. Always these for your environmental variables. Why? If you don't, what happens? Firstly, crying. I speak from experience. Why am I crying? So, okay, so this is an additive effect on R0. Okay. Let's say I just add 3 to the temperature just because I like the number 3. What's that going to do to R0? Mean R0. Gonna drop it by exactly 3, right? Because you're adding effect. Actually, it's the parameter times 3. But what really firstly, z-scoring is a good thing to do anyway, just to, but in stock synthesis, if you don't do it, you end up with horrible correlations between your parameters. And then you run MCMC for, say, 3 or 4 days, and you get 1 sample from the posterior, which is not really very helpful. Then you cry because then you realize you just lost a week of your life. But the cool thing is it's actually remarkably easy to do this. I mean, compared to the old days where you had hard code environmental variables in, apart from Eva's point about, it'd be nice to do a dome-shaped one, please, but that's not available.
You need data to estimate both sides of the dome.
Well, well, yes and no. I mean, we got ourselves in a little bit of a mess with Northern Rock Sole in one of the early versions of, this is not Northern Rock Sole, but what happened was we found a positive relationship between temperature and recruitment, right? And the problem is we then forecasted that into the future. And you ended up with more Northern Rock Sole than you had pollen. And so the solution is either to have a dome-shaped function, or what we did, which was just put a Ricker pulled it like that. But you've got to be, with these models, you do have to be careful about projecting outside of the range of plausibility. So you're sort of dropping off the SXT, as you say, it's dome-shaped eventually.
Right, we usually don't have data on.
But when we forecast for 100 years, yeah. Another really cool slide. Okay. No, it's me. Every time I give a talk, Ian will tell me about that. I'm still using the slides from 1999, and he's usually right. And so I'm trying to say that I've actually moved beyond 1999, which was a great year. I mean, most of you weren't born, but it was a great year if you were born. That's right. It was a great. Yeah, I wish we had another one of those. Anyway, so the models fit the data remarkably well. So the right left-hand side are actually the fits to the survey data and to the fishery CPUE data. Time varying Q, of course, does help quite a lot. That's the good news. The right-hand side is a significant relationship between SST and recruitment. That's on the x-axis. No, that's not. Sorry, that's a relationship between the mean recruitment with the environmental index. So that's basically the mean recruitment adjusted by year. So it's actually SST. And the y-axis is the predicted recruitment. I can actually do, I'll show you in a moment, I can do a lot better for cod. You have to squint, but it turns out there is a relationship there. You're not believing me, are you? I was a little disappointed by this myself, but and then the vertical line that you can see is actually R0. So if you just said what's the expected recruitment in every year in the null model, it's just the vertical line. R0 is a constant in the model. And the dots deviate at least from the vertical line on the x-axis by the effect of temperature. So there is an effect of temperature, but to be honest, still a lot of the variance is coming out of unexplained variables. So this is.
Is it really very much to account for this effect? Because as we say, you can put any environmental variable into that. So.
Well,
because you're accounting for more parameters because you are estimating new parameters with this relationship. So.
Well, okay, so yes and no. Firstly, that's a good question. There are plenty of variables that I've looked at in the past that help. This is significant, right? Statistically significant, and consequential. I mean, believe it or not, this actually makes quite. Because remember, over time, you're moving into this area here, and so. You're going to get your expected recruitment is going to change. So this is one of those consequence versus statistical stuff. But I've got worse things to show. Question.
Hunter, can you repeat the question?
Material can repeat the question.
Is it better to account for this kind of relationship, even if we know that whatever the environmental parameter we put in, we will have a correlation. So.
Well, we won't necessarily have a correlation.
No, but you will find something.
If you use the machine gun method. But I'm not going to do the machine gun method. I'm not going to write.
Your relationship is really for the really low
values, yeah. But when I do forecasts, of course, I've got still my recruitment variability. So my recruitment variability is on top of any environmental. I'll show you results for deterministic projection. So this is the one that I'm still scratching my head. So you all made fun of me 5 minutes ago, right? Same plot on the left-hand side. So I can't remember model. Model D is SST and model H is pH. This is the prediction from mean recruitment. This is the recruitment estimates. Are you happier?
I see the
Are they from the, is the y-axis from the unenvironmental model? Is it from the?
No, no, for the same model. So that's a little annoying. The problem is when you compare between models, the estimates, you sort of can't win because they're from different units. But when I have done that, it looks quite similar. What's really freaking me out a little bit is for some reason the model is fitting the recruitment. So this is these are time series plots. So that looks really good, right? So if I'm publishing this, I'm going to leave that figure out because you can't see that much of a signal until the end. And then it's sort of fitting the data almost exactly. 2020, I go to 2021 for recruitment. But basically from 2015 onwards, the fit is perfect, which means that it's changing recruitment to fit the index rather than fitting the, I was very surprised by this. I've never seen it before.
Are they not selecting fish until they spot, in which case you have no other source?
There's definitely selectivity on smaller. I mean, this goes going back quite a ways, but this is something that I'm clearly looking at because I don't feel, I need to understand this. I've never seen it before, and it's happening for both pH and it's happening for SST. I suspect what's going on is close to where you're going in, is that there isn't much data on those small animals, and it's getting more points by doing this. And I'm not sure how to stop that happening. D is SST and H is pH.
Well, is it, I think it, is it, if this is the only information you have.
Forwards and H.
For those cohorts?
Those are dramatically
models,
right?
I mean, I think that's
Yeah, exactly. I mean, the recruitment is being driven by the environment.
right, but I guess isn't that what Ian is asking? Do you have age data for these last 5
Yeah, we
cohorts?
definitely have age data, but not maybe enough.
What should you be looking at those age data?
Yeah. Good suggestion. Yeah. Apparently, RFSS does that. Yeah. Okay. Wasn't that the professor? Oh no, you graduated. I forgot. Okay. Good point. In fact, this one I think is conditional. Age at length data. But anyway, I need to look at that. So just because you always have to show your AICs and stuff like this is actually not an AIC, it's just the negative log likelihood. And it turns out that, so this is Eastern Bering Sea. I can't remember what the models 1, 2, 3, and 4 are the 4 assessment configurations. And this is the difference between the null model and a model with SST in it. And statistically, for better or worse, the shotgun model might look like a shotgun, but in fact, statistically, with 2 parameters, 10 likelihood units is statistically significant. So I'm still always a little skeptical, but.
are really, really good.
Well, no, but in likelihood units, the absolute likelihood that matters, not the relative. This is a negative log likelihood. So it's 10 log likelihoods, which is, chi-squared 2 is 5.99. Now, obviously there's model weighting and stuff like that, but if you believe the model weighting, which if I didn't believe the model weighting, the whole thing goes, Pac-Man died. So I also did almost a machine gun method for COD because I don't know why. And so we looked at not all combinations, many combinations of M, growth, and recruitment. And the best models are the ones with stars, I think. So this is actually the best model. This is the best model. Block, M, SST, surface pH for recruitment. I suspect even Mathieu is going to be impressed by that change in negative log likelihood from 3858 to 3791. That's 60 likelihood, so that's pretty significant. It turns out that I didn't really focus on model G. I went to model H because I want to be able to forecast SST. So there's actually The block, there is definitely an improvement by using block. So SST itself doesn't do as well as block. But remember, the block was chosen to do best. So it probably, there was some model selection to get the block. So.
I have a question for
Yep.
online. Christine asks, did you look at the predictive skill of the different models?
No. Will I? Yes, I guess I have to. I'm sure NOAA is going to provide more money for me to do this, right? Okay, so ignoring that last question and Ian's question, the next stage was to actually use synthesis in a MCMC mode. And to do that, I used the 80 nuts package, which Cole Monahan developed. So I don't know how many of you have seen this package. It does make doing MCMCs a lot simpler than 80 nut package generally. But what is most useful is you can run stock synthesis models within nuts. And it seems to be a lot better than using the standard Metropolis Hastings version, in the sense that it converges in your lifetime. So those are the commands. So you do need 80 nuts library. This particular, the specifications are very similar to using STAN, basically, tree depth and alpha and all that kind of stuff. The one thing that really helped me from Cole was this call, which you wouldn't see if you were using STAN, metric equals MLE. So that actually seems to use the MLE and the variance covariance matrix in some of the internal calculations. I save the file, and then if you haven't ever played with the Shiny ADMB, I'll show you some outputs from that, but that's really helpful to diagnose your MCMC chain and stuff. Sadly, I did a lot of MCMC tries, and tries I might. The parameterization of selectivity in SS is just too stiff, basically. No matter how hard you try, I could never get to estimate all of I couldn't get a sensible posterior if I didn't fix the selectivity parameters. So I fixed the selectivity parameters. But it turns out I'm not really worrying about selectivity in the future. I'm worried about those link parameters. So here is the output from Shiny ADMB. Ooh, the slides aren't nearly as nice, but so the sort of, the default diagnostics that you start with are the effective sample size relative to the N. In my case, I was basically getting as many, the effective sample size was the number of samples to the posterior. Don't worry about that. The famous R hat, so I did 5 chains. R hat for this particular model is 1.005. Which from a R hat point of view is pretty good. I had about 400 parameters in this model. So it wasn't as if I got it down to nothing. It's hard to see these plots on the right, but essentially these are the posteriors for the link parameters. Essentially this is for COD, the similar ones for the GOA COD. EBS COD are very similar, but basically the posteriors are all on one side of 0, basically. So the whole posterior is where you would expect. Okay. Hey, look, new. Come on, give me a break. Sorry. Sorry.
Still not gonna buy your time share.
You haven't seen some of my the slides that Kiva and Ian went through. The design needed quite a bit of improvement. This is an improvement, right? Yeah. When you start low enough, anything is an improvement. Okay, so again, back to Fish 555. Terrence, pay attention. We're going to do some SS here. So obviously you can do forecasts in stock synthesis. In particular, you can do the standard projections are FMSY, F some biomass target, some SPR target. For this project, this was actually partially funded by the Ocean Acidification Project within NOAA. And one of the reasons why you saw pH in the analyses, because he who pays the piper gets the variable. But I also was interested in projections based on economic considerations instead of just pure yield considerations. So I'm going to talk a little bit about forecasts where we use maximum economic yield to do the forecasts. So the economic model is very simple in this particular case. What we did was we, normally when you, MSY is defined as the F that maximizes the equilibrium catch, right? What we did was we basically turned it into a net revenue function. So we take the catch, we multiply by a price, which in this case is time invariant, even though there may well be supply-demand effects. And we subtract off the variable costs, which we assume are proportional to fishing mortality rate. These parameters are a little funky. This one is price. This is easy. This is price per unit catch in kilos or tons or whatever. This thing is cost per unit fishing mortality, right? Which normally you would work in effort units, but in fact, the model doesn't use effort explicitly. So there's another analysis that turns F into effort, which then turns it into variable costs. And for those who use stock synthesis, there's a new, as part of this project, we developed a new definition of MSY, which is actually MEY. And for those people who are doing the stock synthesis class, you get to specify, this is the forecast file, which you should be familiar with. One is the standard calculate, the standard outputs. In synthesis, if you put in a 5 here, you get MEY rather than the standard stuff. So if you're doing an assessment for the West Coast, you would be choosing, what would you be choosing? 3, I think, for what you guys are doing. Target biomass. Then you specify what you define as MSY units. In this case, it's 4 using profits. And then you have to enter the fleet, for each fleet, what its cost per F is, price per catch unit. And this last input basically allows you to avoid including fleets in MEY. So for example, in synthesis, you can have discard fleets, which really, I don't think that adds to profits very much, but in fact it affects MSY. MSY includes discard, but you probably don't want to maximize your discards when you're trying to maximize profits. And you certainly don't want to include the discard fleet when calculating MEY, because we'll probably say get rid of the discard fleet because it doesn't land. So it's actually very easy to set up the projection. Okay. What time is it? Okay. To quote Churchill, the end of the beginning is complete, but the beginning of the end is yet to come, right? So we're past the end of the beginning, but not the beginning of the end. I have to have one Churchillian saying in every talk. This is sort of like, as well as something from the Roman Senate, but not in Latin. Although we did have Latin during the SFC meeting on the weekend. Well, stuff was correctly translated. Carthage must be destroyed into Latin during the meeting. Anyway, so in order to do projections, there are a number of things we have to specify. The model configuration, so basically which stock assessment model, how the environment affects the parameters, so that's, SST is affecting recruitment. And now we get into projections. So which of those Earth system models am I going to use, and which configurations? So just so you can get a practical sense, so when I'm showing results for the Eastern Bering Sea, I'm going to have 4 model configurations, so the 4 stock assessment models. I'm only going to show results for 1 environmental model, that's the best one. I'm going to have 3 Earth system models, the standard 3, and 2 emission scenarios. So how many is that? 4 times 3 times 2, which is 24. Right, so for a given harvest control rule, I'm going to have 24 possible catch series, reflecting the uncertainty in the true model, in the emission scenario, and in the SSP, right? Because we don't know which of those is going to be true. I'm going to show results for 2 harvest control rules, one the normal 45 tier 3 harvest control rule, but with an FMEY target, not an FMSY target. And I'm also just going to look at constant F just as a reference. So in one case, you reduce the F as the stock drops. In the other case, F is constant.
So that's 48 models for
That's
Bering Sea.
That's 48 catch series,
Catch series.
right? And well, I'll tell you what I'm going to do. So that's the simple projections. The complex ones even more. Okay. So now I'm going to jump, just because I'm pedantic, I'm difficult, want to make it as difficult as possible to understand the talk, to Gulf of Alaska cod. So, but there's a reason for that. So here I'm showing Gulf of Alaska cod, not the Eastern Bering Sea cod. And what I'm showing are different models of reality and harvest control rules. So let's let's start up here. So this is the green line and the red line are 2 models that have only having M being time variant. Okay, so this is biomass and this is catch. I think this is the 45 control, if I'm not mistaken. And what you see is for the green line in these first 2 panels, the green line is the model we have block M, right? So M goes up in 3 years and then comes down to a base level. And what you see is that under that scenario, biomass reaches a constant. I can't see anyway, I have glasses, so it really doesn't matter. You'll see that biomass reaches a constant, and so does catch, right? So if you have nothing going on in the future, everything stabilizes, which is what it should do. The blue lines are actually the reference point. So this is the target reference point and the limit reference point. So going below the second blue line is back. And you can see here is the effect of SST on natural mortality going forward. So given that temperature is increasing, you've got a declining trend in biomass and hence catch, right? So the difference between those 2 is simply what is the effect of of temperature on M. Okay. Then what I do in the bottom panels, I now start to change. I've got models in the past, but I'm now changing the model used in the future to include temperature effects on growth and temperature effects on recruitment. And here you can see that this variance starts to increase even more. So depending on what you assume, you can get some radically different projections into the future. And all these models were, I won't say highly supported, but they were all supported by the data. But, and this is important, each of these are deterministic projections. There's no recruitment variability. There's no model uncertainty. So this is just purely the uncertainty due to the how do you link the environment to parameters, and which model do you forecast? You with me? That's because he gave me series. That's what you get out of. Yeah. The temperature has. I mean, it's not forced, but it is not just random arbitrary.
And Andre, just to make sure I understand, because I cannot read the figure.
Yeah, I can't either.
Can you, from the top to bottom, so
okay.
What is changing for each row?
Okay, as I remember, and if you read the paper, you would know, but I forgot. So this row is, no, well, it didn't help me, so. Okay, so top row, 45, 40, the tier 3 control rule. Second row, constant F. Third row, tier 3. Fourth row, constant F.
Great,
Okay? Then the difference between the red and the blue is how is M modeled, time blocked or linked to SST. And then in the, oh, sorry, that's not true. This is 40, 45, 45. But what I'm changing here is this is FS126. This is 585. So this is changing the, no. Sorry. Now I remember what these figures are. Hugh is losing all faith in me. Okay. If you read the paper, you'd know. So 45, constant F. Okay. There, each of these has 6 lines. The green lines, which are more optimistic, are the 1, 2, 6 projection. So the sort of things go well-ish scenario. The red lines in the future are the 585, which is we don't do anything.
business as
Right.
usual.
I think it's slightly more negative than business as usual now. But
So the colors on the top be something different than the colors on the bottom, is that correct?
yes, the first 2 rows and the second 2 rows. But within within each block of 4, they're the same models. And then the difference between the solid line is block M, and the dashed line, which you can barely see, is SST drives recruitment. And then the dotted line, which crashed spectacularly, is pH drives recruitment. So remember, you already saw that as Ian said, you know, if you put pH in, your recruitment is already low, right? In the past. And so when you forecast, it goes to hell in a handbasket. I'm still very skeptical of those pH results.
Why?
Well, because I'm not seeing them in the 2 areas. Why would pH affect GOA cod and not EBS cod?
And you said that those came from the OA project in Alaska?
Well, the reason I looked at it was
Yeah.
because it's the OA project, but it came out of the same. You want to tell us where that pH comes from? Another source, right?
Well, so because you have pH for the bearing and pH for the gull, right?
Right, but pH for the bearing comes from the ROMS model.
pH for the bearing comes from the ROMS
But
model.
GOA, it comes from you.
Yeah, because in the GOA there is no pH in the ROMS.
Right.
So no, I was just gonna say that pH in the GOA comes from the raw Earth system models, which have a pretty coarse resolution.
What's the difference in absolute pH between the various samples from Alaska? Like, is one of them more acidic than the other?
I don't know on average. I know that bits of the bearing that are pretty acidic already, but I don't know the average. But again, I'm using all of these as indices, so I've z-scored.
Well, sure, but like, the effect.
Right, a lower pH already.
If it's, yeah.
So yeah, I mean, all of these, this is a work in progress. Yeah.
Rick has a comment.
Sure.
He says pH is a proxy, pH affects ecosystem, ecosystem affects cod.
Yeah, but I want to see it in both ecosystems. Anyway, what was I going to? Okay. So that was the simple projection. Now we get to the complex projections. Okay. So the projections I showed you in this, that was for GOA College, and they were projections for models, environmental indices, etc. Each of those projections is based on the assumption, step back, given a catch series, okay, the biomass implied by that catch series is based on the same model that was used to create the catch series, right? So it's like a perfect match. The catches match the biomass. But of course, we don't know which of those models is correct. So what I'm now going to do is, and so basically that underestimates risk because you're assuming that you know perfectly the correct model. So what I'm going to do now is I'm going to do what we call in Australia a cross catch projection. So I'm going to take the catch from one scenario and apply it to the other, to all the scenarios, right? So if you get a catch series, let's go back here. So basically you take this green catch series, right? So this is the catch series. This is the getting updating and stuff. That's the catches that you would set if you believe the green model was correct, right? But what would happen if you applied the green catch series when the red model is correct? We know what the answer to that is. It would tap, right? Because the red model is more pessimistic than the green model. But of course, the whole point of doing this is that, in some sense, all of these projections are part of the uncertainty. We don't, if we knew if we knew that MyROC was right, well, we wouldn't do it right the other, right? So we don't know which model is correct, and we also don't know, at least at this point in time, which SSP is going to be. The only thing we do actually know is which harvest control rule we tested. So in my first version of the paper, I actually had uncertainty in the managers. They didn't know what control rule they would use, but it turns out that's not really uncertainty. They will know what they're going to do, but we don't know which is going to be correct. So what I'm going to do here is I'm going to firstly forecast each catch series for each model. So that is, I think, 1,300 combinations, because there's not quite 48 catch series and 24 models, I think it is. But it's over 1,000 combinations. But the problem is that's still deterministic. That's ignoring the variability in the parameters of the model and in the random variation about recruitment and growth. So then what I'm going to do is I'm going to do 1,000, whatever it is, 156 simulations, but I'm going to sample from the posteriors and include processing. So the final set of projections are going to have model error, which assessment model is correct, which environmental model is correct, which Earth system model is correct, which emission scenario is correct, the uncertainty in the parameters of each of those models, including the environmental link parameter, and the uncertainty in recruitment and growth. I believe this is the most uncertain projection ever done in fisheries. No, that's what's cool. Okay, so because now we're back to Terence, this is your class again. How do you do this in stock synthesis? Well, firstly, you don't search for two. So in synthesis, which I discovered the painful, you know what happens when you run 1,156 projections with the wrong value in the forecast file? You end up with a hell of a lot of output files that don't have anything in them. So you've got to get this right, it turns out. So at the end of the forecast file, there is a bunch of options which allows you to specify how you're going to project forward. And 2 is what I use. So this is the dead catch. It turns out there's no discard in the card assessments. So basically what I did was I went to 1,500 and whatever it is, input files, forecast files, and put in the catch. I fixed the catch. So instead of using a control rule, I was forecasting with pre-specified catches. And yes, I did write an R script to do this because going into 1,500 and whatever it is input files was going to be too much. So this projects forward under constant catch. So what do you get? So now this is where it gets quite hot. Okay, so now you've got to change your worldview. Okay. Normally what we think about when we talk about uncertainty is we're projecting a model forward, right? And there's uncertainty in its parameters, and there is uncertainty in the processing, right? That's what we normally do. What I am going to do is I am conditioning on a catch. So I'm saying, given a catch series, I am going to show intervals that capture the uncertainty due to all those other things. So when you see the uncertainty bounds here, these are uncertainty bounds for one catch series for all of the models. So close to your point, Sabrina. So the first one here, these are deterministic. I haven't got the parameter uncertainty in yet. So I actually wrote it down. If I knew that Kiva would ask me, what is row number 1? I wouldn't know. So this is what happens if we base our catch series on no effect of SST on growth and recruitment. So we're assuming that growth and recruitment won't change. Okay. That gives me a catch series, right? Because that's one particular model. And this is the intervals you get over all the models going forward. So the green line is the target and the red is the limit. So what that is saying is if we manage under the assumption that there, and there's no feedback here, if you manage on the assumption that SST will not affect anything, in fact, there are no environmental effects, essentially you are guaranteed a disaster, right? So essentially, it really doesn't matter which model is true, you always end up crashing stock if you base your management on this is in some sense the most optimistic scenario because it's saying that nothing changes.
Andre, what's
Yep.
the difference between the gray and the black?
Okay, gray is a 50% interval and black is 90%. This white stuff?
I think that's gray. That's gray.
Oh.
Sorry.
Yeah, she looked at the computer.
Yeah.
Okay.
No one needs to give the university more money to buy projectors.
There's a really weird looking figure on it.
Yeah.
But I think we were looking for like 10 years.
I've produced the same figure for 10 years, yeah. Hey, I'm good. Yeah, no, let's not go there. So have you finished making fun of my figures?
Figure's fun, it's fun.
How can it collapse so much? Because I mean, for some of your models,
Yep.
they are almost to zero at the end of the time series.
Yeah, because you're taking, all you're running on is recruitment. I mean, basically but remember, even, let's go back one.
You said there's no feedback?
Well, there's no, I'm not simulating doing more assessments. That would be, it's not a full MSE. So it's set and forget management, which is not obviously realistic. So you wouldn't, but basically it makes the point that you actually need feedback management.
How many years is it going out?
2099, which you can't see because I cut off the x-axis. The second plot is, and I got it right, catches are based on MyRock 126. So this is actually, of the environmental models, it is the most optimistic. So it's the one that says biomass won't decline as much, right? So you've got to think about these models in the context of what they imply. So, but what does that mean about the catch series from MyRock 126? It's the biggest, right? Because MyRock 126 is the most productive in the future. So it leads to the highest catch, right? Or higher catch, which you then apply to a whole lot of models, most of which are less optimistic than MyRock 126. So if you manage assuming MyRock 126, you think things aren't going to be that bad. But when we project forward, we're going to project forward, including the scenarios where things are bad. You see what's going on? So you're assuming that things will be good, but on average they're bad. And this bottom one, which looks the least worst, if you want to call it that, is when you base your management on the worst case scenario, which means the lowest catches, right? And then you apply it to all the models, and you can see this is the only one that has a biomass at the end somewhere near the limit reference. So essentially, none of these are optimistic, but there's clearly a need to think about what your strategy is and how you take into account the uncertainty when you're going forward. So in one simple sense, by basing management on the worst case scenario, you're the least likely to essentially crash the stock, but of course it has the lowest captures as well. Okay, so the next step, of course, is to look at the width of the intervals. So now it's almost at your point, Sabrina, that yeah, we now know how little we know. So this is the same calculation that I just showed you, but now I'm including samples from the posterior for the parameters and the process area. And not surprisingly, things get wider. The little bars at the top which don't look anything like they do on my screen, is the probability of dropping below the limit reference. And the little red line is 100%. So you can see that even in this scenario, about well over half the projections would be below the limit reference. Okay. Oh.
I like the last figure that you have. That's cool.
The good news is they crash so much, you've got lots of space in the top right corner. That's right, you've got lots and lots of space. Yeah.
I mean, is this figure telling us that even if we manage EBS code based on the worst case scenario that we can think of, EBS code is still gonna be under the green line?
Even when you use a strategy that switches the catch-all, you don't. I'll get to that at the end. Basically, the negative effects on recruitment dominate the positive effects on growth. So the growth temperature increases growth, as you would expect, but temperature also reduces recruitment. And on balance, you just can't win. I haven't got any catch equal zero projections here. They would drop down quite significantly. So short of having a hatchery for cod. And the interesting thing is this result comes out of the single species models, but also, for example, the Seattle model, which is a multi-species model. So it's a consistent pessimistic piece of news. I don't want to get into this. So what this is just other performance metrics. So what I've done here, it's just a different way of looking at the data. So this is the probability. Each of these things is bad. The higher it is, the worse it is. Each of these is the model used to derive the catch series. And these are the models on which to base management. So this is all 28 catch series, because there's 4 catch series based on the null model. Because remember, the null model doesn't have an environmental link, so it's not sensitive to viral. But what you can see is the higher this is, forget the variables, each of these is a sort of probability of something bad happening. And you can see that managing under the null model clearly is the worst case scenario. And these higher spikes that you see tend to be if you believe that 126 is, if you believe things will be good, they're not, on average, they're not. So you get the higher risk. So it takes your brain a little bit to get around that. If you manage based on things looking good, they actually end up being bad. Well, it's like, investing in, what was that bank they just went? They had great interest rates. Yeah. And what's that other, it's basically a pyramid scheme. You're betting on things working. Okay, so what time is it? Hopefully, I should be finished by 2:30, right? On
I have
average.
a question from Rick.
Yeah.
If you're going to get to this later, we can.
I doubt it, because I only got 2 slides.
How do we build in learning, reevaluation, and recalibration of a model every 5 years?
Yeah, so we buy a very big computer. So yeah, no, clearly, what these risks are clearly overestimated, because there is no attempt there's no concept of updating the biomass estimates every 5 years. There's also no concept of updating the parameter distributions going forward, and assessing, for example, in 5 years' time, we'll probably update the SSPs as well. So, we'll, like already we've changed some of the SSPs from CMIP 5s, I guess it's the emissions model. The climate models change slower, but yeah, even between ACLIM 1 and ACLIM 2, the scenarios have changed. So we'll be updating those over time. Hopefully we will start to say that 585 is less likely than 126. But my guess is probably, anyway. But no, Rick is very, very correct that we have not got full feedback or any feedback in these calculations.
And I have one other question.
Yeah.
Grant just asked about Seattle, because you mentioned it really
Yep.
quickly. So you've also done these projections to see.
I haven't, but Kirsten Holzman has. For EBS cod, we've done similar calculations with fewer control rules, same sort of tier 3 control rules, and And they all end up with the same conclusion that, given the balance between growth and recruitment, even with multi-species effects, things go negative. Okay, so I wanted to finish at 2:30, so I'm close, but discussion. So the sort of, I've got the good, the bad, and the ugly, although the slide is just ugly. So firstly, the sort of good is that there are common drivers in the two cod stocks, which I consider to be a good thing, that if you're getting the same driver, the same direction of the driver in the different areas, but not always. Why does pH affect Goa cod, but not EBS cod? And obviously, in the case of this example, only Goa cod had that huge push of marine heat wave that gave contrast in temperature enough to detect an M effect. Although I haven't really looked at that much of temperature and M in the EBS model. So that's the sort of, for terrence, that stock synthesis can easily handle random variation and the link to the environment. So grow stock synthesis. It's still difficult to get a cheap MCMC. I have to say, without coal, I would have never got anywhere. But it turns out we need coal, super coal, or changing selectivity modifications to get full convergence. It's amazing how fast NUTS is when you set up a model that is fairly well structured. So it's like 20 minutes to get a full converged 5-chain MCMC. Even with that same model with the Metropolis Hastings would take ages. I've said this already, increases in temperature are predicted to increase weighted age, but decrease recruitment. And in this model and in others, essentially the recruitment effect is outweighing the weighted age, so the net consequence is down. Rick's point, harvest control rules assume more or less Rick's point. Harvest control rules that assume no future effects suck. They're going to fail to conserve the stock. But the general message is, everything seems to be pointing to declining productivity generally. I was actually going to put a final box in to pick up Rick's point, but I forgot. And that is, ultimately the feedback thing is important, but that's a little computationally beyond anything I can do. And then where am I going? I still want to understand what's going on with Goa cod and the suggestion by Ian of how about you look at the fit of the data would be a good idea. I've got to update the environmental variables again and rerun because I've rerun already. We've got some economic stuff to do. And then we've sort of touched on already looking at some more environmental drivers for EBS cod to make both species look at quite a few other things. And of course, I'm looking for more suggestions from you guys. But the final slide, mainly because Doug Butterworth would be very upset with me if I didn't put it up, is the final warning: what the data giveth, the data taketh away. So, my sort of ultimate warning with this work is we really need to avoid the sort of embarrassment of saying EBS cod is going to decline, recruitment is related to temperature, pH is going to kill all these animals off, and then 3 years' time, material repeats the calculation, says temperature is really good for cod, and I'm old enough to remember people doing things like correlating recruitment with every single environmental variable that they could ever think of, and then spending a week working out why the Mariner score is going to drive recruitment. It's related to the temperature that's generated when we score runs, and that affects the circulation, which then feeds into the Gulf of Alaska, and it really makes complete sense to me, right? So I haven't included in the model the pirates. You know what I'm talking about? Everyone, didn't you know this, that pirates cause global warming and hence are causing...
I didn't see that paper.
It's actually quite a strong correlation. If you plot number of pirates against sea surface temperature, there is a strong negative correlation.
What is the data about the number of pirates?
Is it global
W
or
Disney
regional?
first column. And then if I put pirates into the cod model, it probably wouldn't do too badly. So in fact, you know, this is like when I was teaching the baby stats class. I mean, I take the students down this path of increasing incredulity to make them think about spurious correlation. So the cure to global warming is clearly what? Blackbeard. We need more pirates. And I will stop there. That is a really bad projector. We should get a new projector.
Now
You got the money.
Sorry?
Now you're job anywhere.
Oh no, is this our projector?
Well, this is the SAPS one.
Oh, okay.
Without your influence downstairs, these are the ones I can get.
There's going to be no coup d'etat, just for you to get better rooms.
I mean, I think first thing is better mic.
How about you guys improve? The technology needs an upgrade, so let's get some better. But yeah,
I guess I have a few comments, but Laura, the most overriding comment for me is you talk about sort of the economic component, wanting to make things realistic by voting MEY, and yet you have a 100-year projection on a completely exturbated stock where nobody would go out fishing, both because management would shut down fishery, but also it wouldn't be economically valuable to fish for Punt if they were, really.
yeah. Again, that's the feedback thing.
So I feel like this is something we often do, where we focus on realism in one zone, but then we have, sort of totally unrealistic projections within a different dimension. I don't know what kind of rig solution in your bigger computer, I guess, is the best one.
Yeah, well, I mean, it is and it isn't, because if environment follows one of these models, given the way it feeds through in more ways than just updating, because if growth is a function of time, that means FMSY is a function of time, which means FMEY is a function of time. And eventually, I showed this in another paper, FMEY actually goes to zero. Because once your expected profits go to zero, the optimum is not to fish, right? So that's another component of feedback that you could look at, but obviously I didn't. There was a paper as one of the, I think was it Northern Roxol that I looked at the time series of FMEY. So what I did was I calculated FMEY in multiple years in the future. You can see, unlike MSY, which is just the maximum of the yield curve, the cost effect really pushes it down quite quickly. So if you did that feedback and updated MEY, it would brittle some of that.
Jim has a question. Is your speaker on?
I don't know.
Jim, can you try talking?
Hi. Can you hear me?
I'll turn my speaker on now.
Give us a minute, Jim.
Speak.
Speak? Oh, thanks. Great talk, Andre. Thanks for doing all the work for NOAA as usual. Really appreciate it. Yeah, just it wasn't clear when you had to fix the selectivity. Were those posteriors being used for the MSY calculations?
Yeah,
it seems like
that's a corner I had to cut. So the selectivity going into the future is essentially the last 5 years of the MLE hindcast. So I haven't captured the uncertainty in selectivity. Right now those are blocked. So you need to find some way to simulate those going into the future, and I haven't really thought about that. So yeah, that's certainly another source of uncertainty that you could build in.
Yeah, I was wondering the interaction that might occur with different age compositions, selectivity being a function of kind of the age, population age composition, and then how that might cascade onto other aspects of your calculations, basically.
Yeah, I mean, it certainly would, because if selectivity was in some sense changing in a directional sense, that would change the FMSY and FMEY, because obviously selectivity determines the yield function. So yeah, I mean, again, that's please provide more money and I'll do something.
Didn't you do this for free though? So just do it.
Double your income.
But it's ironic that selectivity is one of the few non-stationary processes in the model. You had to take it out in order
To get the
model the non-stationary processes.
Yeah, I mean, well, so there's two issues there, and both of them important. One is quantifying the uncertainty in path selectivity, which I couldn't do. The next is how do you forecast selectivity? Because right now they're just modeled with blocks, right? So if you were, I don't know what assessment it is, but if you linked, for example, the length at 50% selectivity with an environmental covariate, then that would make a lot of sense. But how do you, so particularly within in SS, I'm sure Rick has got some tricks. But if I wrote my own projection model, what I might do is say, if I've got some blocks in the past, well, I'll resample a block or something. But when these block things are really hard to forecast unless you can turn them into a covariate.
You can't, using the no U-turn algorithm, and you still can't estimate it like the U-turn, you really estimate it.
It's the stiffness problem. It's that essentially the surface is just so nasty. You can the MLEs, I mean, with jitter and stuff, you do get back to the same answer. Yeah. But the algorithm just does not like parameters that have very high derivatives. I mean, and that's true of all these algorithms. They're just it's like when I started this whole MCMC thing, and Ray and I didn't know what MCM stood for. We thought we wrote the paper. We thought, okay, well, let's fit two models. Let's fit a age-structured model and let's fit a production model. We'll fit the production model because it'll run really quickly at MCMC, and the age-structured model will take a long time. Well, completely wrong. Mainly because the parameters of an age-structured model are sort of close to linear, whereas a production model very, very, yeah, exactly. And in fact, what I found with some other stuff is, like normally in a production model, you remove the catch. What I'm now doing is subtracting F, where F is an estimated parameter, times B, and that flattens the surface, which normally you'd say is bad, right? Because you don't want a flat surface, but when you're sampling with MCMC, you want to be able to cross the surface. So it's a structural thing with the way we've set up selectivity.
But I give them an in about then the assuming asymptotic normality is.
Yeah.
Right.
But I don't know the answer to this, but some of these AR1, the AR type sort of non-parametric selectivity patterns might actually be part of the solution. So it's one of those things where adding more parameters might actually make it a little easier to get convergence. But I haven't tried that. But clearly, the parameters of double normal are just so interconnected. Yeah.
It just like the thing that got me thinking about like the different effects of pH that you could see between the Bering Sea and the Gulf. As it applies to temperature is that like the way that the changes in these environmental covariates translate into biological changes more often than not is actually mediated by consumption, right? Except like there will be cases where if it's too hot, all the eggs die. Then there's nothing to do with consumption. But if it's not like one event, and if it's a trend, then it's predation that mediates a lot of these. So that's where a more like multi-species, more like Seattle could help kind of disentangle, because consumption is something that could in fact be different between the two areas, right?
No, I agree.
What they eat is a lot lower in one of the two than. And implicitly, you capture some of that in your model, obviously, right? Because it is a function of, say, temperature. But if having an approach that kind of accounts for that in a little bit more explicitly could answer some of those questions.
Yeah, I mean, Seattle doesn't deal with growth at the moment. Growth will be modeled the same way, but again, in principle, consumption should affect growth, which it doesn't in Seattle. It affects mortality, but not growth explicitly. But you know, I guess where I'm coming from is avoiding the. I've lived through the machine gun era where, you know, I've got SST, so I'm going to correlate SST because I've got it, and I've got, you know, these are the environmental variables I've got, so I'll just keep doing regressions, find significance, and then come up with a reason. One of my favorite stories is a graduate student was sitting in a defense, and my professor, who's met Doug Butterworth, he's a character, should we say, and he's not a very forgiving character. So Maddie's giving her final presentation for her PhD defense, and she's done it. She's done the machine gun method, and she did 200 correlations and found 4 significant ones. We talked about how, excuse me, can you talk about the other 4? How did you know there were 8? She says, well, 200 on 0.05. And then his other question is, you know what type 1 error is? And that was the end of that defense. So that was, he wasn't very, the student was, I don't think we ever saw a student again. But yeah, don't be that person. But yeah, the problem is the field is really pushing this stuff, and without thinking about it really strategically, I think we could end up with egg in our face. Again. Rick was around in those days.
But not before telling you that there are better selectivity options available.
As he would. Well, no. Yeah, I'll tell that to the COD people. Okay, how are we doing?
We don't have any questions at the moment, just a couple great talks. Thank you. If anyone else has any questions, feel free to drop them in the question bar or raise your hand and I can unmute you. Include pirates in that.
Yeah, that's true. We have to include that in the revenue part of the function. Revenue to pirates. No, pirates are an important part of fisheries management. No, well, more Indian Ocean. There used to be a de facto MPA. It's definitely, well, I'm sure you know. What was that paper that Ray criticized that said that MPAs affect species anywhere in the world? You know that paper? That was one of them. Yeah, no, this was really, Cody really didn't like it. Anyway, I think we may be done.
All right, well, thank you everyone for coming and thank you, Andre, for giving us a great talk. Oh, hold on, before we go.
Someone else said it wasn't a great talk.
No, Lauren Rogers says, following on Haley's question earlier, I encourage you to read the ESPs for the 2 stocks. Lots of background there on mechanisms to help avoid the shotgun approach.
Excellent.
And with that, we will conclude today.
Followed by a clock. Okay, guys. What's today? Tuesday.